Hi. In this video, we're going to explore some of the tools that Matlab has for solving linear systems. In class, we've discussed three important tools that we can use to solve systems, linear systems. All of these are related, but different approaches that address different aspects of the problem AX equals B. One of these is Gaussian elimination. We have discussed how we can start with an augmented matrix and then following first through forward elimination to an upper triangular form and then carrying on through back substitution to a reduced row echelon form, we can, when there's a unique solution, simply read out the answer from the last column, and when there are multiple solutions, deduce the general solution from the structure of this matrix. There's also a checkpoint built into Gaussian elimination for when we don't have a solution. We've also discussed the matrix inverse for square coefficient matrices, which are quite common because they correspond to systems where we have equal number of unknowns and equations, which is a situation that often arises. When such a system is non-singular, when A has an inverse, when there is a unique solution, that unique solution can be found simply by multiplying the right-hand side by the inverse. And LU decomposition is another way of, in some sense, encoding the steps of Gaussian elimination that we can use to efficiently solve for multiple right-hand sides for the same system over and over again without needing to redo all of Gaussian elimination. More generalizable than the matrix inverse as it's applicable to non-square systems, to systems without unique solution, and so on. And LU decomposition, we phrase it as this, a permutation matrix multiplied by some matrix A equals L times U. And this can be rearranged to give us two systems, a lower triangular system and an upper triangular system that are very easy and fast to solve compared to a full non-sparse system. Okay. Matlab has built-in functions that let us handle all three of these with essentially none of our own work. The computer will do all of the work for us. The function that handles Gaussian elimination is RREF, which standing for reduced row echelon form. The matrix inverse is computed by a function called inv. Both RREF and inv take a matrix A as an argument and return the reduced row echelon form or the inverse of that appropriately and gives error messages when the inverse doesn't exist. And LU decomposition is handled by the function called, not surprisingly, LU. It has a slightly different form of how we write it. We have to enter the matrices we want to store the answer into, returns an L, a U, and a P from this matrix, so this LU decomposition. One thing that I would like to note here, and I will mention again when we discuss LU decomposition in more detail, Matlab's implementation of LU decomposition also applies row exchanges when they are not strictly necessary. When we work through this by hand, we generally only exchange rows when we have a zero in what would needed to be a pivot position. There are lots of reasons why it can be useful to exchange rows when the pivots are small but not actually zero for numerical reasons, and Matlab does this. This is an important nuance to remember. The LU decomposition that it gives is correct. It may, however, be slightly different than what you get by hand. Okay, now all of these systems start off with a linear system. They're tools for having a linear system. You need to make sure that we're clear on how we store a linear system in Matlab. Right? The first step is always to define the variables to be used. These are variables not in the context of a mathematical model where we're looking at the symbols that correspond to the unknowns in the problems, but variables in a computational context, the kind of names that we are going to use to store information and refer to them. For a linear system, we've already discussed how a system of equations can be converted into a matrix form of AX equals B, a coefficient matrix A and a right-hand side vector B. This is the form we are going to use to store a system in Matlab, define a matrix A and a vector B. We can store these vectors with the Matlab code as follows. Create a variable called A and store in it this matrix. Square brackets say we're dealing with a matrix. The entries of the first row separated by commas, and then a semicolon to move to the second row. The entries separated by commas, a semicolon to move to the third row, and the third entries. This will store this coefficient matrix in A. For B, we want this to be a column vector, so we use 5, semicolon, move to the next row, 7, semicolon, move to the next row, and 2. This will give these two values stored. This is perfectly okay Matlab code, but we will often find, especially for larger matrices, that writing everything in a big long line is really hard to look at. It's hard to double check to make sure that you haven't made mistakes. It's visually not very clear to somebody reading. We can make this easier using a trick, using ellipses. Ellipses, 3 dots, are a tool that Matlab uses to convert multiple lines into one big line. When Matlab reads this, it reads A equals square bracket 1, 1, 1, semicolon. Continue the next line as if it was the same line. 2, 3, 4, semicolon. Continue the line as if it was the same. 0, 1, 2, and bracket. No more ellipses. Now Matlab knows that the line is ended. And so it does exactly the same thing as the previous line. Right? This allows us to organize our matrix in the same way we look at it on a piece of paper and make sure that everything is looking very clean. These semicolons, as a reminder, act as line breaks. They separate the rows. You have to have these in here, even with the ellipses. The ellipses just say continue the line. If you didn't have these semicolons, it would make one big row matrix that had all of this information. These commas are separating the entries within a row, the columns. They are not actually necessary. You can leave just a space there, and Matlab will read it exactly the same. That might look a little bit more like the matrix you write down on paper. I personally find that the commas help organize things a little bit, and so I like to use them most of the time, although sometimes I don't. Okay, so that says how we define a linear system. We can also build up things from these bases. Sometimes we're going to need an augmented matrix. We don't need to define an augmented matrix separately. Once we have our coefficient matrix and our column vector, we can simply construct a new matrix. Say we want a matrix that's first block is A and its second block is B. Standard, really, block matrix notation, and everything will work cleanly. If we try to do this and B is either not a column vector, let's say it was a row vector instead, or if it had a different number of rows than A, then an error message would be given here so that you know something has gone wrong. In this example here, I've also added semicolons at the end of every command. Right? This semicolon on the outside of the matrix definition is the last character. Simply suppresses the output to the command window. If you don't have this, the value of A gets written to the screen and the value of B gets written to the screen and so on. This often, especially for defining your variables, can make things messy, and so putting these semicolons can make it easier to find the things that you really want to find but are not necessary. Okay, now let's get into the first of the three functions that we're interested in, now that we know how to define the linear system. We use RREF, which stands for Reduced Row Echelon Form, to have Matlab do Gaussian elimination for you. It will convert the matrix you give it into the reduced row echelon form through a sequence of row operations. Right? Remember that when we're solving a linear system this way, we need to use the augmented matrix. And so we can either do this in what we call an inline format, just say RREF, and I want to give it the matrix AB. Or if it's clearer to you, we can define the augmented matrix first, and then after storing that, simply give that defined matrix to RREF. Both of these will have exactly the same output. Now, when we do this, the answer that gets returned is simply the reduced row echelon form, exactly the same as if you had found this working through by hand, but without actually having to do that work. You use it in exactly the same way that you would if you had done it by hand. You should always check for inconsistency. Is there a row that is all zeros except for the B column? If there is, then the system does not have a solution. Are there any free variables? Remember what is your coefficient block, count your pivots, identify your pivots, and ask, are there free variables? If there are no free variables, then the last column contains the solution. If there are free variables, we need to express the pivots in terms of the free variables to get a general solution in parametric form. This is something best doing simply translating back into a system of equations, not within Matlab, and writing the form down. Okay? So this is really a tool to reduce the effort involved in performing the steps of Gaussian elimination, but doesn't change what you do once you get that form. You can use RREF just like this, in which case it will output the answer to the command window. You can also store the result in a variable. This will create a matrix called R that has that matrix in it. If you don't have a semicolon, it will also get written to the screen, but it's also saved in case you want to look at it or use it later. I should emphasize this is saved not in a file that you can come back days later after you've exited Matlab and look at it. It is saved within the memory of Matlab, within the workspace, so that you can look at it a few minutes later if something gets overwritten on the command window or something. Okay. Just as a final sort of representation of seeing how RREF works in actual Matlab instance, here's a screenshot with a simple Gaussian elimination problem. In fact, the problem that I had outlined on the screen. We set up our matrix A, our vector B, our augmented matrix, and then I solve the system, RREFM. I also add a second right-hand side and now try to solve this system. We can do this in an inline form, RREF, on the matrix A.2. This lets us get the solution to this. This is one good reason why I always like to define things as a coefficient matrix and a right-hand side rather than just defining the augmented matrix up front. This allows us to swap right-hand sides very easily. What do these answers look like? They come up in the command window. They are clearly reduced row echelon forms. Pivots here in columns otherwise all 0. The pivots are in exactly the same position. The coefficient block is exactly the same in both forms because they have the same coefficient block. But our interpretation of these would be very different. In this first case, we see there's a row that's all zeros, but a 1 in the last column. The right-hand side of 572 does not have a solution. On the other hand, the right-hand side of 273 gives a row of all zeros. That's perfectly fine. There's a free variable. This is a system we would need to solve in a parametric form. Okay. We showed examples of using Matlab to solve a problem with a standard augmented matrix. You can use RREF to solve any problem that you would normally use by hand Gaussian elimination for. You can solve multiple right-hand sides like we saw in a worked example video. We do this simply by creating an augmented matrix that has more columns. Right? The answer to this will have all of the information needed to solve the system. The last 2 columns will now both be right-hand side columns that can solve for both the right-hand sides. We can also compute a matrix inverse this way using Gauss-Jordan elimination. We set up our matrix as A with the identity matrix. Just to sort of be clear, how would we normally do this if we were working through this by hand? The matrix we would want to set up would be AI, where I is exactly the same size as A. Right? How do we execute that in Matlab? Matlab has a command, I, spelt like the eye on your face, that you can either give 1 number or 2 numbers, and it will return the n by n identity matrix if this is either a single number or if these are the same. Size is a command Matlab has that will tell you how big a matrix is in terms of the number of rows and columns. So size A gives m and n for an m by n matrix A. Right? So what does I size A do? It looks at A, it asks how big is A, and then it creates an identity matrix of exactly the same size and puts that in the block. Exactly what we want to do here. If we then run RREF on this, we look at the answer. If the A block now contains the identity matrix, then the second block contains the inverse. If the A block does not contain the identity matrix, because there's 0 rows in it, for example, or 0 columns in it, then the A must be singular and not have an inverse. That's RREF. How do we use the inverse function? If we want to compute a matrix inverse, we use inv, standing for inverse. Remember that when we're applying inverses, we generally want to use a coefficient matrix, not an augmented matrix. So work with the coefficients, not the augmented matrix. This is another good reason why in defining the system, you separate out the coefficient matrix and the right-hand side. We can compute the inverse if we just want to write it down on paper simply by using inv A. Much more frequently, we will want to use the answer in Matlab, in which case we would want to store the answer. So write something like A_inv. This is just the name we're going to use. You could use different names for the inverse and store the inverse in that. Now, remember that A must be square and non-singular for the inverse to exist. What happens if we ask Matlab to do something it shouldn't be able to? Luckily, Matlab often gives a very clean error. If I try to invert this matrix, I've written not one line. This is the matrix 1, 2, 3, 4, new row, 5, 6, 7, 8. This is a 2-row, 4-column matrix. It is not square. If we try to write the inverse, Matlab will return in the command window something like this. Error using inv. Matrix must be square. Very clear error message. This might often happen if you accidentally give an augmented matrix rather than a coefficient matrix to Matlab. What happens if the matrix is square but singular? How about I define a matrix A, 1, 1, 1, first row, 1, 1, 1, second row, 1, 1, 1, third row. 3 identical rows, clearly a singular matrix. If we try to compute the inverse, Matlab gives warning. Matrix is singular to working precision. What this means is that it is, so Matlab does everything, it does almost everything numerically. When it says it's singular, it says that as far as it can tell it's singular. Maybe if you go really, really small numbers, many decimal points, maybe there's some non-zero rows in there. Matlab can't make sure. It's a question of, is this really 1, 1, 1 and 1, 1, 1, or is this 1, 1, 1 and 0.99999999999, 0.999999999. Right? So we get a warning that is still very clear. It gives an answer where it actually says that all of the entries are infinity, which clearly doesn't make any sense. A clean warning, however, that this is a singular matrix. You do have to be careful, though, because sometimes the warning isn't quite as obvious about what's going on. If I give instead this matrix, 1, 1, 1, 2, 2, 2, 3, 3, 3, this is still obviously a singular matrix. I've just taken scalar multiples of two rows of the previous matrix, which is also singular, right? This Matlab gives a different error. Here it says matrix is close to singular or badly scaled. Results may be inaccurate. And then it gives something called a condition number that lets you assess just how close to singular it is. Right? It gives us an answer. Right? It gives us an answer that when we actually look, if we read this, this says 10 to the 16 times these values. It puts huge numbers in there. Right? If you compare what happened in the previous case, it gave infinities. Here it's giving numbers close to infinity. It should be read as the matrix is singular. Matlab can't clearly define things as singular, non-singular in the same way that we can. The way that it analyzes things is different, at least when we use the inverse. And so when you use the inverse function, it's trying to do things numerically. It will try to find an inverse. Look very carefully to make sure whether these warnings are telling you that you really shouldn't have. If you want to check for whether it really is singular or not, it actually can be cleaner to use the RREF function on this and see that you get 0 rows. That will give a cleaner answer on singularity. Now, when you do have an inverse, it just returns the inverse cleanly and you can use it. And we can use this inverse to solve any problem just the same way that you would use them if you were computing it by hand. We can use the inverse to solve problems with multiple right-hand sides. If I have AX equals B1, B2, and B3, the solutions to each of these can be found by multiplying the inverse by the appropriate right-hand side. If I've already defined A and all of my vectors, or on my right-hand sides, we can then store the inverse, A equals inverse, A inverse equals inverse of A, and then use this stored answer to get x1 by multiplying it by b1, x2 multiplied by b2, x3 multiplied by b3, and so on. We've seen how we can find the error in a solution with the inverse. If ax equals b, ax plus delta x is b plus delta b, then delta x is given by A inverse b, just as x is given, ax inverse delta b, just as x is given by A inverse b. We can do this the same way. Compute the inverse once, store it in a variable, use that variable to solve the system, and use that same inverse to get the error. Once again, just to show you this actually in the context of Matlab, we have a screenshot with a brief script that computes a matrix inverse for the matrix with rows 1, 2, 1, 1, 1, 1, 2, 2, 1, 2, 3, 3 different right-hand sides, and a delta B. We can compute this one calculation of the inverse, and then use this to solve one right-hand side, another right-hand side, a third right-hand side, and the error. Right? To give a sense of what this outputs, when we run this, as I've scrolled up so we look at the top part of it, we see the inverse is printed out as a matrix. This is actually what the inverse is. Then the first solution, and if we were to look down, we'd see all the rest. The workspace, we can see we have our solution x1, x2, x3, and delta x all here. That's the inverse. What about LU decomposition? LU decomposition can also be handled directly by Matlab. Ignore the spelling error here. Right? One important thing to note is that LU decomposition in Matlab is always done with the possibility of row exchanges. It is doing a PA equals LU decomposition. Right? And it will often apply row exchanges even when it might not need to in a strict sense. Right? This means two things. First of all, a by hand decomposition may give a different result, and you always need to keep the permutation of matrix around. You need that. Right? Once again, LU decomposition is something we do on a coefficient matrix, not on an augmented matrix. Remember that. So the basic syntax is a little bit different here because we're going to get 3 different matrices as an answer instead of just one. We need to specify where Matlab should store those. Here I'm just using the symbols LU and P. You can use other names for them. We need these square brackets here to let Matlab really clearly know that there's 3 different answers that this function is going to spit out, and to put it into each of them as appropriate. Right? Now, the LU function in Matlab is a bit interesting because it's what we call an overloaded function that will do lots of different things depending on exactly how you use it. One thing that changes how it behaves is how many matrices you ask to get back. Right? This is one of the reasons why it's really important to remember that in Matlab, LU decomposition is going to give you LU and P. The standard form for using this, you define a matrix here, LUP in square brackets equals LU of A. We'll do the LU decomposition, and it will store in L a lower triangular matrix that has ones on the diagonal, in U, an upper triangular matrix that may not necessarily have ones on the diagonal, and a permutation matrix P that will have exactly 1, 1 in every column and exactly 1, 1 in every row, but corresponds to swapping rows. This is what the standard form is. This is how you should usually use it. If you take a look here and your P looks like the identity matrix, it means that Matlab has returned an LU decomposition that didn't need row exchanges. If this is not the identity, then row exchanges were needed. Okay? This is the standard way Matlab, this is the standard form I would recommend you using. Let's say that we didn't give that. Let's say you forgot that you needed to put the P in there and you just asked for 2 matrices. What would happen? If you just give LU 2 matrices on the left, it gives different answers. It gives the same U. It gives a U that is an upper triangular matrix with exactly the same values as the previous version, but it doesn't give a lower triangular matrix. It has rearranged things. Actually, if you compare to the previous result, what it's done is it's actually swapped the last row and the first row of L to give this form. Right? Why did it do that? Because this permutation matrix said swap the first row and the last row. When you only ask LU to give you 2 matrices, what it does is the first matrix it gives you is actually the product of P and L. It found the lower triangular matrix, and then it's multiplied the permutation matrix by it. You can deduce what the lower triangular form must have been because there's only one way that you can exchange these rows to get a lower triangular matrix, but it's something that you would have to do by hand. Right? I don't recommend you usually use this form, but be on the lookout for it in case you accidentally use the wrong syntax. If you only ask Matlab to return 1 matrix for the LU decomposition, or if you just use LU decomposition by itself without putting anything here on the left, then Matlab actually does a really funny thing. It returns a matrix that has all of the information in L and U, but merged together. Actually, this isn't quite right. There should be a -I in here also. So let me correct this right here, and I'll correct it on the slides. Right? Why does this work? Well, L is lower triangular. It only has things on and below the diagonal. It also has 1s on the diagonal. So L minus I doesn't lose any information because the L always has 1s on the diagonal, and we're left with 0s on the diagonal and above, and only the information of L below, right? So if we think about what was our L here, 1s on the diagonal, 0.75, 0.25, negative 0.4286, right? What does this matrix have below the diagonal? 0.75, 0.25, negative 0.4286. If we add to that L minus I, which only has things below the diagonal, U only has things on the diagonal and above. So adding that together gives on the diagonal and above exactly what we had in U, 4, 5, 6. Negative 1.7, negative 3.5, and 0. 4, 5, 6, negative 1.75, negative 3.50. Right? It has all of the information in L and U, but in this kind of funny looking matrix. Again, all of the information is there except the permutations. Note that we do not have the permutations in here, but it captures a lot of the information in here. Again, I don't recommend that you use this, but be on the lookout for it. This is what's happening if the common error here is just giving LUA without telling it where to store the results. Okay. So just as a reminder, the standard form that you should use for LU decomposition in Matlab is this one. Make sure that you use a left-hand side, and make sure that you use a left-hand side that has 3 matrices listed. Right? Also, remember that Matlab very often performs row exchanges when it's doing LU decomposition. You need to pay attention to the permutation matrix. Now, unlike Gaussian elimination, where the applications are very, very clean and well suited to looking at things by hand, and the matrix inverse, where also we can do applications where you can sort of work through some of the things by hand or directly use it in simple Matlab code. LU decomposition is more a tool for solving real systems, for solving big systems. Right? As a result, using the results of decomposition, LU decomposition, to actually solve problems efficiently is something that goes a bit beyond the scope I really want to cover here. For the purposes of your knowledge in the class, simply knowing how you can use Matlab to generate these LU and P matrices is perfectly sufficient. Okay. Just as one final sort of reminder or sort of piece of information, we can take a look at what LU decomposition looks like in a real context. Define a matrix. Use this form with 3 output variables. If you do, you will get your L, your U, and if you carry on down. There are other ways you can use this to get PL and U, or to get this X, which is this merger of the two. And these have places where they can be used, but we're not really going to focus on those. So this has now wrapped up a discussion introducing how we define linear systems in Matlab cleanly and efficiently, and how we can use the 3 different tools. Gaussian elimination, essentially, moving to a reduced row echelon form through RREF, matrix inversion with the inv function, and LU decomposition with the LU function. Hopefully, this will give enough of an introduction that you can explore using these tools in Matlab for helping to validate your homework solutions or to solve interesting other problems. Thank you, and goodbye.